Hello, workforce development, radiology students. I'm going to do kind of a mini lecture. This course is pretty rapid and pretty much self-taught as you go through it, but I thought that those of you who might benefit from a lecture, um, that you can utilize these, but it is not required to watch them. But again, just there if you need to use them, as this is an online class. When studying, I download all the PowerPoints. I read them through. I go over them. There's notes in the margins, and read the book, right? Put it together, going over each chapter, the PowerPoints, and what's in the book. And that will really prepare you for the quizzes that are open book. Physics, this is the first module. What's in the first module is a bit heavy um, in learning, right? So physics is hard for some people to wrap their heads around, but this is chapter 2. So we will kind of go through a little bit of this together. At the beginning of every PowerPoint, there are learning objectives. So if you can answer these questions or follow the prompts, that you will be doing really fine for quizzes. But again, you have the open book option, so definitely utilize that. And this is the introduction. It's really just telling you, we're going to be talking about the actual X-ray machines, how X-rays are produced, fundamental concepts of atomic or molecular structure. This stuff gets really heavy, especially if you're not into science or have taken college courses in the sciences before, but we will make it through. So basics, right? Matter and an atom. Hopefully you understand what matter is, right? Anything that occupies space and has mass. And an atom is the fundamental unit of matter, right? Really small. You cannot see it with the naked eye. And so again, just basics for physics. The atom has a nucleus. It's orbiting electrons. And you could see here, this is a really basic kind of drawing of what an atom is. I find Khan Academy, like if you don't know these basics or taken science in high school, it's really good to buff up on that. The nucleus is comprised of protons and neutrons. Protons are positively charged. Neutrons have no electric charge, right? They're neutral neutrons. And most of the atom is empty space. The number of protons in the nucleus of the atom determines its mass number, how much it weighs. Again, I'm not going to go really deep into that. Just know that on the periodic table, the different weights is listed on there, but that's not what we're really trying to learn in this radiology class. But you do have to have a basic understanding. Is the nucleus of an atom affected by X-rays? No. And the orbiting electrons are. So really, when you're taking X-rays, that radiation is really affecting things on a molecular level. The outer layer of electrons may be disrupted during radiology, right? So the radiation hits it and then changes it slightly. Again, radiographs are very safe, and we'll talk more about that. But it does have some effect on our body, our atoms, right? And too much radiation can affect your body by overloading or changing those atoms. But electrons are tiny negatively charged particles, right? Not able to be seen with the eye, and the shell located closest to the nucleus has the greatest highest energy level. So as they go out further, less energy, right? It's more effort for those uh, electrons to have greater energy. And this is again a kind of description of the electrons and just how it produces energy. And it becomes really important because again, too much radiation can be disturb the body, right? You don't want radiation poisoning, which you do not get with dental radiation. The molecular structure, atoms can combine with others. So again, this is kind of basic physics, but they bond to one another, right? Simple example, caffeine or H2O, right? H2O is hydrogen and oxygen, and they combine together to make water. And before you are able to understand how X-rays are produced, working knowledge of how ionization and the difference between radiation and radioactivity is really important. So ionization is normally most atoms are neutral, right? A neutral atom contains an equal number of protons and electrons. The atom is completely filled to its outer shell. It is um, a whole atom. And then when radiation hits it, it has gains an electron and it has a negative charge. So an atom gains or loses electrons, becomes electronically unbalanced. So you can see here the radiation hits the atom, it sends an electron, removes the negative electron, and gives it a positive charge. The atom then is unbalanced, and we call that ionization. So we have cations and anions. So one is cation is loss of electron, and anion is gain of an electron. And radiation in dentistry, specifically X radiation, is used and is not radioactivity, right? So we are creating energy through space in waves or particles. Radioactivity is when something is unstable or spontaneously disintegrates or decays, right? So we are not causing that. You don't take a dental X-ray and things start to decay or the radiation stays there. We're using radiation to get a picture. Very important difference. Again, walking through, I won't go over every slide. You can self-study, but it is divided. Ionizing radiation is in two groups, right? We've got the particulates and the electromagnetic radiation. And particulate radiation is tiny particles that possess mass and travel in straight lines, right? So we've got the alpha, the beta, and the gamma, right? So you can see from this photo that alpha stays, right? The beta can travel through, and gamma rays is wave-like and can travel through both the paper, the hand, and into the concrete in this photo. Electrons, right? So those beta particles are fast-moving. Cathoids, we're going to talk about cathode versus anoid, and cathode rays are streams of high-speed electrons that originate in an X-ray tube. So right, we're going to talk about the parts of an X-ray tube, and the cathode is high-speed electrons. If you see something highlighted in red, it means it's important. Pay attention to it. You need to grasp this concept as it might be on one of the quizzes. Right, so again, if you want to look to your book, table 2-1, it'll talk more about protons and neutrons, right? Accelerating and not accelerating. And the propagation of wave-like energy, right, is electromagnetic radiation. We know about electromagnetic radiation. That's what a lot is in dental X-rays or microwaves, right? So it's oscillating electric and magnetic fields are positioned at right angles to one another. And they have common characteristics. They might be ionizing or non-ionizing. They might have different size wavelengths. And so that really will determine the type of radiation and how strong it is moving through. All right, particles, right? So particle concept characterizes those electromagnetic radiation in terms of discrete bundles, and they call this energy photons or quanta, right? Photons are bundles of energy with no mass or weight, and photons travel at waves of the speed of light through space and time. I know this is, I mean, it's probably bringing you right back to like, sixth or seventh grade science class, but those are what particles are, right? And then particles have waves. So electromagnetic radiation has waves. Wavelengths are measured in nanometers. The shorter the wavelength, the greater the penetration. And conversely, the longer the wavelength, the less penetration. So see those waves, and the apex of one is shorter and more, right? So the short wavelength, 1, 2, 3, 4, the longer wavelengths, 1, 2, 3, right? So that will really determine some information about the radiation. Velocity is a term, and it means the speed of the wave. Wavelength is the crest of one of the top of the wave to the other. And frequency is the number of wavelengths that pass through a certain point at the given time, right? So some radiation is going to go slow and some is going to go fast. So X radiation is high energy ionizing electromagnetic radiation. That's what it is. Somebody much smarter than me a very long time ago discovered that, right? And X-rays are weightless bundles of energy, and they penetrate, causing that ionization. So when we take a dental X-ray, it is going through the atoms, is causing ionization, but we're getting that picture at the end of the day. So some really important parts of the X-ray components to know. And when you come into lab, you will get to see them, touch them, use them. But we have the control panel that is on the wall. And it has different settings to it. So depending on, and we'll talk about density or how maybe thick a person's bone is how much radiation you need to penetrate that person to get an image that is readable. On the panel, also the little film packets when we did conventional and the computer is digital. We all take digital X-rays in our offices. It's very rare to have conventional X-rays. We have an exposure button, and that is our control panel. It's always on the outside and should always be 6 feet away from where you're standing, unless you're using something called a Nomad, and we'll go over that in a later module. With the actual in the operatory X-ray machine, we've got the extension arm. It usually bends in different ways. And then the tube head, which is where the radiation is made from energy into radiation. And then the long, the long area on the front of the tube head is called the PID, position indicating device. So as we talked about the control panel, it kind of makes all the amount of radiation very simple. There's a lot of math to that. I know I don't like doing a lot of math. A lot of folks will put, especially old school radiation panels, will put them on one setting and it kind of stays on that setting. But it's really important to change the control panel depending on where in the mouth you are radiating. It's going to tell you the time, the kilovoltage, the milliamperage. It's got an energy source, right? So we use electricity. On this panel, these are the panels that you'll see at STIC. The top areas here is if you want to manually change what we call KVs and MAs, and we'll discuss that. The second row is wet teeth. So the first two, the first icon is a central or lateral incisor, right? Pretty thin teeth and bone areas. The next is a canine. Canines are a little bit thicker, so you need a little bit more radiation. The middle one is what we're bite wing, right? Our checkup X-rays, and we'll go over that. Then with the roots down, that's the mandibular tooth, and then maxillary tooth, right? So when we're pressing the control panel, we're really controlling how much radiation is being sent out for a picture. The next row is if it's a computer or conventional, and then the body size. So, we say a lot of the time the pedo or the child setting, but, if you've got a little old grandma with thin bone, you might not need as much radiation to get through. If you do too much, and we'll talk about it, the picture is too dark. And if you don't do enough radiation, the picture is too light, and we need diagnostic radiographs. So that extending arm bar comes right out of the wall, and part of the control panel. There should be a panel on the outside too, where you are an exposure button, and it has all the wires going from the electricity, right? The wall, whatever electricity is being harnessed into radiation and energy. When you hit that button, it goes through a process and radiation comes out. But the articulating arm is so you can move it around where you need to go. And it is attached to the tube head. And the tube head is a metal housing, right? So it contains the X-ray tube that produces the dental X-rays. It's inside of the tube head. It has transformers, protective tube, high voltage components, and it has insulating oil. Okay, so that insulating oil, because radiation and that electricity moves so quick, it creates heat, and the insulating oil makes sure that it cools down, prevents from overheating. You will notice, I think, in some older models, especially when it's very humid out, some of that oil can leak out of the PID, and then I keep the tube head and the PID pointing up straight to keep that oil in there. But that oil is very important. It's not like you have to refill that oil. There's usually enough oil, and oil becomes more when it's heated up. So within the tube head, it has the oil in it, filters, and the X-ray beam. The X-ray tube is the heart of the generating system. It's inside the tube head, the X-ray tube. It's in red, so that's going to be important. And there's a transformer that alters the voltage from the electricity into radiation. So you can see there's a lot of verbiage on the tube head, right? The power supply, there's an aluminum filter, aiming cylinder, collimator, power supply, the oil that's within the tube head, and outside the arm here, we call that a yoke. The tube head is attached to a culminator, right? So there's been different shapes, round or rectangular, and there's aluminum discs in there that will filter out, right? We're really trying to get all of this radiation to come through and be very specific to where it is going. So those filters are going to filter any of the scatter radiation or any radiation and kind of hone in exactly where we need it to go. The culminator restricts the size of the X-ray beam, right? So making it intense. And the PID aims and shapes the X-ray beam. So we're literally putting in a sensor, and we'll talk about that, and then using this while it's on the tube head, lining up the PID. And when we hit the exposure button, the electricity turns into radiation and captures the density of the teeth on the sensor. There is a glass vacuum tube. It's about 1 inch in diameter. It's got leaded glass housing, a cathode, and an anoid. So again, this is really important. You can see the anoid here. This is where the electricity, the positive ions come out and shoots over to the cathode. There is a tungsten target and a filament in there. It bounces off that and through the lead culminator and out of the PID, and that's what creates the radiation and controls the radiation to where we want it. So very important, cathode and an anoid. So the lead glass housing, so again, here with the anoid, prevents X-rays from escaping in all directions. If it goes everywhere, scatters about, we're not going to get the density we need. We're not going to get the radiation that we need. So that leaded glass vacuum tube really points it in the right direction. It's called a window, and it permits the X-ray beam to exit the tube and directly towards the aluminum discs through the lead culminator and through the PID. So again, there's pictures in your book, and a lot of verbiage and definitions, and you just need to be familiar with what's going on as assistants. Sometimes we have to maintenance these things. We have to understand where the electricity is coming from and how it all works. It's very important. So now the cathode. You have to know the difference between a cathode and an anoid. But the cathode supplies the electron necessary to generate the X-rays, right? So the electricity goes through a tungsten wire and comes out the cathode. And the purpose of the cathode is that it supplies the electrons necessary to generate the X-rays. The hotter the filament becomes in the cathode, the more electrons are produced. And the focusing cup, so the Menundum cup, keeps the electrons ready near the cathode so that the instant the exposure button is activated, the circuit becomes complete and the electrons travel across the X-ray tube to the anoid. So it's going to start at the cathode, going to press the exposure button. All that energy is going to be harnessed. It enters the anoid and goes down and becomes a useful X-ray beam. So now we have the anoid, and that's the positive electrode. It consists of the tungsten plate. And again, so right here, it shows you this graphic. The electricity has now been generated by the cathode. It hits the tungsten target, converts X-ray electrons into X-ray photons, and then comes out of the PID, and we're harnessing that. So cathode, negative, anoid, positive. So we talk about catnap, right? So it's just a way to use the beginning. And this is open book, so you don't have to memorize it. But cathode creates the energy, hits the tungsten target on the anoid, turns into X-ray photons, and comes out the PID and creates an X-ray. So there's other elements, electricity, currents, transformers. I won't get too much into that, but there's a lot going on in that tube head. And we need electricity, right, to create radiation. So whether it comes from a battery, and we'll talk about that, or electricity on a wall, there is a power supply somewhere. There is an X-ray tube. Somebody has set this up. This is not something that us as dental assistants are setting up. And the radiation board comes through our offices every couple of years and makes sure that everything is running and there's no radiation leaking. It works on a AC/DC, so direct current or alternating current. And so this shows you that the dental X-ray tube acts as a self-recidifier, and that changes AC into DC when producing X-rays. So very interesting stuff, I know, guys. So amperage versus, so MAs is amperage. So amperage is the measurement of electrons moving through the conductor. So how much power we are sending through. And they say that this is an MA. So right on our panel, it'll give us a number, and that's the quality or amount of radiation that we are sending through. MAs directly influence the number of electrons, so how much striking the target, hence the number of protons produced, right? And that's called thermonic emission. Again, really sciencey stuff, but that's thermonic emission. It's heating up, it's coming out, it's emitting. Increasing the MA or decreasing the MA, again, is going to alter how much radiation or how less radiation. So when does that matter? Why we have those settings on the panel, right? So if somebody is a thicker bone or a bigger person, they need more radiation to get a diagnostic X-ray, where somebody that might be smaller doesn't need as much. So we can manipulate that by hiring or lowering the amperage or the MAs. We then have voltage, right? So we have KVs and KVPs, and it's the only component that will influence penetrating ability, right? So it can determine what it's going to get through the KVP. And it's the efficiency of the X-ray. So it converts the kinetic energy into X-rays and heat. And again, we can manipulate the KVPs going higher or lower. to adjust on how dense or how much radiation or how fast it's coming out to get a good X-ray picture. But again, the new systems, you're putting it on the settings that are out there. You don't have to worry about the kVps or the MAs or do any kind of math, which is very nice. So rule of thumb is, again, you don't have to do math, but if you're increasing either the MAs or the kVps, you need to adjust the other one. So again, if you come, your offices, a lot of offices don't touch that. They don't go near adjusting the kVps or the MAs, and we just automatically let our panels do that for us. This is information on the circuits and the transformers and really how much energy or volts that it takes to get radiation. This slide talks about transformers, right? So it's really the nitty gritty of how that electricity is coming through and creating that radiation and how it's traveling. And now production of dental x-rays in 12 steps. So electricity, this is really what you need to know. This is the guts of it. Electricity from the wall outlet supplies the power to generate x-rays. The current is directed through the filament circuit into that step-down transformer and in the tube head. The filament circuit uses 3 to 5 volts to heat the tungsten filament in the cathode. Thermonic emission occurs and releases the electrons. The electrons stay in an electron cloud until the high voltage circuit is activated. When you push the exposure button, the high voltage circuit is activated. The molybdenum cup in the cathode directs the electrons to the tungsten target in the anode. And when the electrons hit the tungsten target, less than 1% of the energy is converted to X-rays. The remaining 99% is lost heat. It is a lot of steps to get 1% of that energy. A small number of X-rays are able to exit the X-ray tube through the unleaded glass window portion of the tube. The X-ray travels through the unleaded glass window, the tube head seal, and the aluminum discs. The size of the X-ray beam is restricted by the lead culminator. So again, we're focusing that beam, that 1%. And the X-ray beam exits through the tube head at the opening of the PID. There is a great video if you want to watch that. I'm a video person, and sometimes it's very helpful to see videos. So now there are different types of X-rays and energy. So there's general or breaking radiation or characteristic radiation. And look at those waves down there. So the shorter wavelength, higher frequency, higher energy, that's gamma. And then as it is longer wavelengths, lower frequency, lower energy, it goes into radio waves, microwaves. So you can see where X-ray is. You need quite a bit of frequency and energy to capture that X-rays. The term breaking is the sudden stopping of high-speed electrons when they hit the tungsten target, right? So it breaks in the anode. And most X-rays are produced in this matter, right? So it goes not one, but many interactions with the target. You're going to hear me say scatter. So sometimes even that 1% that comes out, some of the radiation scatters. And that's what we're trying to control. We're trying to make sure that it's going right into the tooth. A lot of, especially older folks, get nervous with X-rays and they're going to tell you, I don't want X-rays. It's too much radiation. You get more radiation from eating a banana than you do a dental X-ray from sleeping next to somebody. Dental X-rays with the technology have a lot of low radiation, and we have science that has really allowed us to pinpoint where that radiation is going and how much of it is going. So general characteristics, high speed inertial. So again, it talks about it, but we have primary, secondary, and scatter. So the primary, and you'll need to know the differences. The primary is the penetrating X-ray that is produced at the target of the anode. Secondary is the radiation created when the primary beam interacts with matter. So primary is that first radiation. Secondary, the primary beam interacts with matter. And then scatter is a form of secondary radiation, and it's been deflected by its interaction with matter. So it is gone off and has scattered. some interactions with radiation, right? So sometimes there's no interaction. Sometimes there's absorption. Sometimes we call it Compton scatter, and sometimes it's coherent scatter, right? Compton scatter, it just flies everywhere. And that's what we try to avoid. That's why you have to stay 6 feet away, because if you're closer to that, the scatter is going to hit you, and you can only take so much radiation as somebody who is dealing with it a lot in a year. And we'll talk about that later on. So with no interaction, the X-ray passes through the atom unchanged. Nothing happens. These photons are responsible for producing densities on a film. Okay, it makes it happen. It's unchanged, leaves the atom unchanged, right? Then there's absorptive and photoelectric. So the X-ray photon is completely absorbed in the matter or the tissue of the patient. So it's traveled from radiation into the patient, it's staying into the patient, and changing the patient itself. So this is another graphic that kind of shows you the different absorptions, the photoelectric effects, right? So it's the total of X-ray proton energy. The ejection of an electron is called photoelectron. So atoms absorbing of a material. We have Compton scatter, where the ionization takes place. The the photon collides with a loosely bound outer shell electron, giving it part of its energy, and ejects the electron from its orbit. So it's sending some of that outer shell off of the atom. And by doing this, it's releasing energy. So another good graphic, as it's coming in here, you'll see that it gets very messy, but the radiation has hit. It is scattered a photon out, is ejected an orbital electron, and this is Compton scatter. Coherent scatter is an X-ray photon that has its path altered by matter. So it's not ejecting something out. It itself is hitting the mass and then scattering, changing its pathway. So no change to the atom occurs, but the photon itself has bounced off of the atom, and that force has changed. So there's absorption, no loss of energy. The photon is scattered. And again, just another kind of graphic to explain that. In summary, the X-rays are absorbed by interaction with the X-ray photon. All the protein's energy is given up in one interaction, and it's called the photoelectric effect. And there's partial absorption. If there is partial absorption, is Compton scatter. So there are those 4 different ways of radiation. Either it passes through, nothing happens. It connects, and a shell is scattered off. It connects and is absorbed completely, or it connects and it's driven off of its course. This is really important. If you want to take this and go through it, knowing the parts of the tube head is going to be important. You will see that again on probably a quiz, okay? Being able to label it can be helpful. If you have any questions, I know it's heavy material. You can always email me, use your book, use your resources. This video has just been an additional resource. And I will continue to make these videos for all of the PowerPoints available. So thanks so much.